You can cool okay, so is there? Was that not? You can explain what's there? Okay, so Jose is going to explain. He wrote down his answers, so you can go through and explain what you did. Why don't you go in front of the class and explain got this.
Well, this one, we have going from a liquid to a liquid, so that means there's no gases involved, so delta N equals 0, delta V equals 0, that's why work equal to 0. And then it's going from high temperature liquid to low temperature liquid, that's why the Q is less than 0. And then, let's see. Want me to explain what?
Yeah, because you wrote that
So the second one, we're going from liquid to gas, so it means delta, the change in delta N will be positive, and volume is positive, means work is going to be negative. And since we're going from a liquid to a gas, it means temperature is increasing, that means Q has to be greater than 0.
Are there any questions for Jose? For steps C and D?
If C was an ideal liquid, would Q equal to 0?
Yeah.
Ideal.
Only have an ideal gas.
If you have an ideal
Yes, that's a good question because see, we've talked about ideal gases, but not ideal liquids.
Pass the list, Mr.
Yeah, so really when we look at liquids, for an ideal liquid, is an ideal liquid compressible?
No.
So that means if it's not compressible, would delta N change for an ideal liquid? No. So actually what Jose did for step C is correct. So since work should equal 0 for step C. I think, is that your question, Mercedes?
No,
So he's talking about temperature Q.
For Q?
Would Q equal 0 if the liquid was ideal?
Oh, so if we have a high pressure liquid to low pressure liquid, see, you would not be able to use an ideal liquid for a refrigerant because you assume the pressure is the same. Yeah, so this is actually, a refrigerant is actually not an ideal liquid because the refrigerant has to be a compressible liquid. In this case here, if it's ideal, it would not be compressible.
Is it because pressure is proportional to temperature as well?
Now pressure is proportional to temperature when we look at gases.
But,
So we assume that when the pressure changes for a liquid, the volume of the liquid remains the same, therefore the temperature remains the same too. So we're actually saying that if we change the pressure on a liquid, nothing should happen for an ideal liquid. But in this case here, the refrigerant liquid is not ideal, so we can make that assumption. So that's sort of like, you're in the ideal world of academia, school. And then this prepares you for the real world of okay, what about step D? You guys have any questions on step D for Jose? instead of thanks, Jose. So let's thank Jose for. So which step, A, B, C, or D, cools the air inside the refrigerator? Okay, so which step cools the air inside the refrigerator? Yes, let's look at Q. See, Q is this is the only endothermic step. So note that heat is gained by the refrigerant, which means that what's losing heat?
Cold reservoir.
Yeah, so the air inside the refrigerator is losing heat. So step D is the step which cools the air inside the refrigerator. And then let's go back to step B. I forgot that. Note that in this condensation step, note that Q is less than 0, which means that heat is being released. So if you stick your hand in the back of your refrigerator, that's where it's a little warm. And that's where we see this condensation step. Those coils in the back of the refrigerator is releasing the water. That's released. Okay, so I know jobs are hard to find, but I hear that these heating, what's this, heating, ventilation, AC people make a lot of money. So now you know how the refrigerator works. Okay, so we described this phase change. Okay, so we know how air is cooled. Now in today's lab, you're going to make a solar refrigerator, so you're not going to use a compressor. Okay, so you're not going to be supplying work by using a compressor. So you'll start with a cup. Here's the air inside the cup. How are you going to remove heat from the inside of the cup? And here's your hint. So note that in the refrigerator here, we had a phase change involved. So what phase change would be involved so that you can remove heat from the air inside the cup to the outside of the cup?
Ice around it.
Yeah, okay, one way is, like you said, you can put ice around the cup, but that's not involving a phase change. Yes, in other words, your solar refrigerator isn't like using an ice chest when you go to the beach. You're not putting ice in your ice chest and putting something cold in there. You're letting that. Yeah, so yes, that's a good solution, but that's not the solution we're looking for in today's lab. So how can you make a solar refrigerator? So let's say that you finished your undergraduate degree in college and you feel like, you know what? Now it's time for me to see what the world is like, and I'm going to travel around the world. Or you're going to say to yourself, you agree, maybe I'm going to do a Peace Corps mission before I start earning my big salary so that I can be part of that 1%. So, if you work in the Peace Corps, you go to these countries, you help the people in those countries figure out how to move water from here to there, how to build, homes which work better for them, how to make their conditions more sanitary, how to cool their food so things don't go bad. So if you were traveling to some country where they didn't have electricity, how would you help them store food so that food doesn't spoil? So you're not going to say, okay, we'll get some ice and put some ice around. No, that's not for me. Because you're not going to have ice. Salt, so what's salt going to do? Salt in where? So you're going to put salt in water. So you're saying that Are you saying that you're going to take some salt, you'll have water in a cup, and you're going to add salt to it, and what's the salt going to do? So you're right, so we know that when NaCl solid is added to water, we know that that's going to lower the temperature of the water, but how much salt do you need to add to lower the temperature of the water? Yeah, that would be quite a bit. And then you got to keep on, so then once you do that, so for example, I guess what you could do is you could put, are you saying that you could put, here's your cup, which contains the air. So you're saying that you have a second cup where you have the water. Then you add the salt to the water here. So as the temperature drops, that's going to remove heat from the air inside. Is that what you're saying? Or maybe I shouldn't draw that picture. You guys can, I don't want to put any give you any ideas on how this can work. Yeah, so that can work, but maybe instead of using, is there a different solid you could use besides salt, which will lower the temperature of water more than salt does? So I'm not sure if you remember from Chem1A, you looked at hot packs and cold packs. So you remember what was the salt you used in a cold pack? It was George? Yeah, ammonium nitrate. So you can use ammonium nitrate because that will actually cool water more so than salt does. In other words, ammonium nitrate has a more endothermic heat of dissolution than salt does. But then at some point, you're going to get to the point where you can't dissolve any more of the salt in the water. Okay, you get to where it's a saturated solution. And then, what if you run out of salt? What do you do? Yeah, so so you run out of salt, could you just boil the salt off? Boil the water off to separate the salt from the water? And then how are you going to boil off the water? What energy source are you going to use? Fire.
Heat on a stove.
Yeah, so it says here again, think phase change. So note that this doesn't really involve a phase, well, solid to a liquid, that is a phase change. Think, what other phase change could you use?
Evaporation, condensation.
Is it going to be evaporation or condensation? So let's see, if we go back here, which one? This was condensation, and condensation, Q is less than 0, so heat is lost during the condensation, which means that heat is gained by, if heat is lost here, heat would be gained by something else. By the surrounding cubic air. In this case here, a liquid going into a gas, what is this phase change called? Yes, this is evaporation. And in evaporation, like Jose said, this is endothermic, so if a liquid is evaporating, heat is being gained by the liquid. What's lost? What's losing heat? The surrounding, which could be the air. So could you use the evaporation of a liquid in the solar refrigerator? And if so, what liquid would you use? Okay, so how would you design a solar refrigerator using water to cool the air inside that cup? Okay, so you're saying, George, you're going to put, you have your cup of air, and you say there's a second container which has water in it, and how are you going to evaporate that water?
Put it in water.
We're gonna add heat.
That's sort of defeats the purpose. How you can add heat? Can you put it on a hot plate and add heat?
Yeah.
So if you have electricity for a hot plate, then why don't you just plug it in the refrigerator?